Hey guys, okay, so I want to go ahead and take an opportunity to just reiterate what we were talking about today in class and help you guys understand why in this particular case there was no extrema. Okay, so if we take the derivative of the function, remember that extrema is when our function goes from increasing to decreasing, and we can find that by seeing a change in the signs of the derivative, because when the derivative is positive, that means that our function is increasing, and when the derivative is negative, that means that our function is decreasing. So here's the derivative, and critical points, again, are where the derivative is either equal to 0, f prime of x is equal to 0, or f prime of x is undefined. So in this particular case, we don't have any places where that's equal to 0, but we do have a critical point at x equals 0 because f prime of x is undefined at 0. Now, it's going to get to a point where you're going to probably realize here that that means that there are no extrema. But let me explain to you why. Okay? Why does that mean there are no extrema? Well, let's go ahead and do a sign chart for our critical point at x equals 0. And if you look to the left of 0, you're at -1. We can use -1 to test, and we can use 1 to test. If you plug -1 into the derivative, you get x to the 2/3 or -1 to the 2/3. So that's basically -1 squared and then the third root of that. So that's always going to be positive no matter what. And if you plug 1 in, it's also going to be positive no matter what. So why? Well, there's no extrema since there's no change. In 0, it's constantly increasing. So what this is telling me that f of x is increasing all the time. So there's no extrema. Now, think about when f prime of x is undefined. If you're looking at the function, okay, if you're looking at a function, any function, f prime of x is undefined. That means it has undefined slope. That means that the slope of the tangent line is undefined. When does that happen? When there's a vertical tangent, or when there's a vertical asymptote, okay? And when there's a vertical tangent, it'll look something like this. Okay, not even that pretty. I might have made it like a little too pretty there. Maybe a little thinned out where there's a vertical tangent. If there's a vertical tangent, that particular function, like this one, is constantly decreasing. The one that we're looking at is probably something along the lines of, it's always increasing, so maybe it's along the lines of something like that, always increasing. Okay, that could still change concavity. Notice how that's concave down, and this is concave up. But when your derivative is undefined, you either have a vertical tangent or a vertical asymptote. We know we don't have a vertical asymptote because if we look at the function, that function is continuous everywhere, okay? But remember, continuity does not imply differentiability. So it's continuous everywhere, but it doesn't necessarily mean that it's differentiable everywhere. So now let's talk about points of inflection. So, okay, f prime of x is undefined. That means that either we have a vertical tangent or vertical asymptote. This particular graph, as we saw, doesn't have a min or a max, but it is always increasing. If it is always increasing, right, and f prime of x, it's always increasing, and f of x doesn't have any undefinition, it's continuous. That means it doesn't have any vertical asymptotes because f of x is cool and continuous. It means it's got a vertical tangent, which is why we didn't have a max or a min. So if it kind of maybe possibly looks something like this, I mean, we haven't really analyzed it too much, but if it looks like this, it will have points of inflection. So now the question is, where are those points of inflection? So we do the same thing that we did to check for maxes and mins, except this time we do it off the second derivative. So here's our second derivative, and and we find the critical points. Again, the critical points are either where the second derivative is equal to 0 or the second derivative is undefined. Okay? This particular second derivative will never be 0, but there is a place where it is undefined. It is undefined at x equals 0. So we make a sign chart at x equals 0. Okay? And when we make that sign chart, we test to the left and to the right. And we are testing it into the second derivative because it is a sign chart off of the second derivative. So, if we plug in -1 into here, and you take a look, it's an x to the 5/3. That means that you're taking it to the power of 5 and then taking the third root. So if you take -1 to the power of 5, it will remain negative. And then you take the third root, it will also remain negative. If we take +1 to the 5th will be positive, third root it will also be positive. So that's telling me that I'm going from concave down to concave up at the inflection point of 0. Therefore, I have an inflection point at 0 even though f double prime of x at 0 is undefined. And the only reason why it's undefined there is because we have, it's not differentiable at 0. So when we differentiate again, it's still not differentiable at 0. But what does that mean for the original function? What does that mean for the drawing, for the graph of the original function? That just means that you could possibly have concavity. Remember, that graph of f of x we decided was always increasing. And now we know we have an inflection point at 0, -2, and it's always increasing. So that means it's going to change from concave down to concave up. It's going to change concavities. Let me move this right here. All right. It's going to change concavities at 0, -2. And it'll also probably have like a little vertical tangent there, don't you think? Because it's not differentiable at 0. I hope that helps, guys. So let's look at a couple trig ones. All right, so let's take a look at this function. The function is sine squared x plus sine x. We're not being asked to do inflection points, but we are being asked to find extrema from 0 to 2 pi. So we take the derivative. Take the derivative of sine squared x, which we do a chain rule to get 2 sine x, and then the derivative of sine x, which is cosine x, plus the derivative of sine x, which is cosine x. When we are looking for extrema, the first thing we want to do is, after we take the derivative, which we just did, we want to go ahead and find our critical points, which, to tell you again, critical points are where the derivative is equal to 0 or undefined. So we take the derivative, and this guy right here, and set it equal to 0. And when you do that, looks like it's complicated. However, you do have cosine x's, so we can take out a cosine x. And now you have something times something equals 0. So just to show you, you've got something times something equals 0. So zero product property says that you can go ahead and set each of those equal to 0 to solve. So cosine of x equals 0. Cosine of x is 0 at pi over 2 and at 3 pi over 2. So there are those two values. And then 2 sine x plus 1 is 0. So I isolate to get that sine x is -1/2. Well, sine of x is 1/2 at 30 or at pi over 6. So where is it -1/2? Well, sine is negative in this quadrant and in this quadrant, in the third and the fourth quadrant. So since this is pi, and we're doing this all in terms of 6, this, you can kind of call this is like a little pre-calc review here. This is pi, you can kind of call that 6 pi over 6, since we're talking in terms of radians of 30 degrees. So if that's the case, then this one is 30 degrees will be 7 pi over 6. So sine of x is -1/2 at 7 pi over 6. And then over here, and to figure out the radians for that, I do 12 pi over 6, that's my 2 pi. go down 1 to get 11 pi over 6. So these are my critical points: pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. You will then make a big sign chart testing those critical points off of the derivative to check their signs. So I went ahead and set it up with my critical points at pi over 2, 7 pi over 6, 3 pi over 2, and 11 pi over 6, and filled out some values in between. And then I kind of jumped around from testing it into the derivative or into the simplified version of the derivative, either or. It's going to get you the same thing. So I've got increasing, decreasing, increasing, decreasing, increasing. So I have a increasing to decreasing. I have a max here, a min, a max, and a min. If you have any questions on how I got these particular values, just come see me in study hall or ask a peer. It's basically just working with radians and seeing what's in between 7 pi over 6 and 3 pi over 2, what values you can squeeze out from in there that are easy to work with. 60, a form of 60 would be appropriate. So yeah, and there's your maximins, maximins, and then you will take this x value of pi over 2 and plug it back into the original function so that you can find the corresponding y value that is the relative maximum point. So I hope that helps with that one. So let's summarize the steps for finding critical points, increasing, decreasing, maxes and mins, and all that stuff. Let's summarize. So if you're looking for your extrema, first step, you want to find your derivative of the function. Then you want to find your critical points. Again, that's where the derivative is equal to 0 or the derivative is undefined. Little note here, if the derivative is undefined, we have a vertical tangent at that place of undefinition, or we had a vertical asymptote because it was probably a value where f of x is not defined. As a result, you're not going to have extrema there. You can still do a sign chart and test it out, but you'll see the function will either be always increasing or always decreasing. Lastly, if you do have values where the derivative is equal to 0, also known as a place where there's a horizontal tangent, then you'll do a sign chart on the derivative to see where the function is increasing or decreasing. Once you know where the function is increasing or decreasing, you can then find your maxes and your mins by analyzing increasing and decreasing. If you know those x values where you have a max or a min, to find the y value, put it back into the original function to find his partner. So let's talk points of inflection. Alright, so points of inflection, you want to find the second derivative. You want to find the critical points of the second derivative. Again, that's when the second derivative is equal to 0 or the second derivative is undefined. Now you can have a critical point, you can have a point of inflection where the second derivative is undefined. In this particular case, the second derivative being undefined, what that means for the function, if we take a look at this kind of mock-up that I did here, this particular function would have a vertical tangent there. And it can go through, it's going to go through the point of inflection. But what I'm trying to say is, if this was f of x, f double prime of x is the rate of change of the rate of change. So the rate of change of the rate of change is going to be undefined because at some point you're going to hit a vertical tangent. So you're going to have like a 0 in the denominator, so to say. But the slopes of the tangent lines, if we drew slopes of tangent lines, the slopes of the tangent lines, the change of the change is changing. The slopes of the tangent lines are changing. So since the slopes of the tangent lines are changing, then that means that it's building concavity. It's building, a function that's going to hold water or, repel water, whatever, however you remember it. So there is change in the slopes of the tangent line, even though the second derivative is undefined, let's say, at that particular point. within the function, within the original, there's still change within the change. There's still movement in the slopes of the tangent line, because it's the change of the change. It's the change of the slopes of the tangent line when you're looking at the relationship between f of x and f double prime of x. So you want to keep that in mind. You could still have a point of inflection at really either of these two critical points, where when testing extrema, we won't have any when we're looking at the critical points where the first derivative is undefined, and that's because of the relationship between the derivative and the function, and the fact that this makes maxes and mins, not points of inflection. So they're two completely separate beasts that deal with two completely separate things on the function. And we already talked extensively about why, when f prime of x is undefined, why that will not make maxes and mins. And again, feel free to make a sign chart on the value that makes the derivative undefined. Your sign chart is either going to be all positive or all negative, showing, again, no maxes or mins. So you could still make the sign chart. Go for it if you want. You just will see nothing change. All right, let's go back to points of inflection. So again, find the second derivative, find the critical points, make a sign chart off of the critical points with the second derivative to check concavity. And when there's a change in concavity, you have a point of inflection, so if there are any. Yeah, so anyway, I hope that helped, and you can watch this as many times as you'd like to hear my voice. And yeah, let's keep chugging along, guys. You know what you got to do. Have a good one.